Mathematics contains an important study field under the name chaos theory. Chaos theory studies the concept and behavior of highly insensitive dynamical systems. It also studies behavior of dynamic systems in initial conditions, which often turns out to be supersensitive at a very high level. In chaos theory, this concept is referred as butterfly effect, which is the main field of study in this theory, from which various branches are spread and constantly progressing and being developed. Various initial conditions are made because of some numerical errors in computations. These errors provide wildly diverging results for some dynamic systems. This makes it almost impossible to predict the behavior of long-term rendering. This happens even when behavior of the system is determined by initial conditions of very same system and no random elements are involved in process. Dynamic systems with such conditions are known as deterministic. In simple words, it can be said that such deterministic behavior, or say nature of any kind of dynamic system, is not able enough to make them predictable. Such deterministic behavior is known as deterministic chaos, or just chaos. The whole theory of chaos is based on this simple fact. Each concept of chaos theory is based on these handful statements. Thus, an attempt was made by Edward Lorenz in order to describe the main concept of chaos theory in a single definition. According to him, present can determine the future, but approximate present cannot determine approximate future. Many natural systems such as weather, climate, etc. follow the rules of chaos theory. They possess the same chaotic behavior as described in chaos theory. Not only natural system, but some artificial systems or system that contains artificial components also follows the same chaotic behavior. Road traffic is a great example of such artificial system since it contains multiple artificial components that are not a part of nature. Chaotic mathematical model is analyzed in order to understand such behaviors of natural and artificial dynamic systems. For such analyzing process, analyzing techniques such as recurrence plots and Poincare maps are implemented. Following is a list of fields and disciplines in which chaos theory is applied or is applicable: meteorology, sociology, physics, environmental science, computer science, engineering, economics, biology, ecology, philosophy. These are the fields in which chaos theory has been successfully applied, that too with expected results. There are many other fields in which research is still going on about application of chaos theory. Deterministic systems are main subject of chaos theory. Chaos theory holds a great concern about these deterministic systems, especially those systems that behavior can be predicted, that is within the scope of principle and related concepts. In the beginning, such chaotic systems tend to be predictable. Later on, they turn out to be random. It means that chaotic systems are predictable until a specific amount of time from their generation. This amount of time can be derived from three aspects: level of expected uncertainty in the forecast or simply prediction, accuracy in the measurement of the current or last available stage, Lyapunov time, which is the time scale fully dependent on system dynamics. Following are some examples of Lyapunov time. Chaotic electric circuits, 1 millisecond almost. Weather system, several days, yet unproven. The great solar system, 50 million years, most accurate since we cannot test it. In chaotic systems, uncertainty in the forecast keeps increasing exponentially. The increment level keeps rising as the time flows on. The more time is passed, the more uncertainty should be expected. Thus, according to mathematical perspective, if the forecast time is doubled, the uncertainty will increase more than square value of its current level. According to this concept, chaos theory says that accurate prediction is hard to achieve if it is made after a time interval which is double or triple than Lyapunov time value. A system is said to be random if any meaningful prediction cannot be made. According to this description, anyone can understand that chaos theory is all about predictions and its accuracy. Many concepts in chaos theory describe how technical predictions can be. Some other describes how inaccuracy can be reduced and accuracy can be increased in those predictions. This is the main base for each concept of the theory. The learner of this theory will study how this concept is applied in various subjects and fields. Sources for chaos theory can be found in many other theories: pure mathematics, pure physics, theory of computer science, theory of environmental science, economic theory, biology, and many other concepts and fields. Chaotic dynamics. Generally, chaos means the state of disorder. Ignoring its general meaning, chaos theory defines the term chaos more descriptively using better precision. No mathematical definition of chaos is yet developed. Those available are not accepted by mathematicians. Definition of chaos given by Robert L. Devaney is the most commonly used definition presently. According to this definition, the dynamic system, which possesses following properties, can be defined as chaotic system. It should respond sensitively in various initial conditions. It should act as mixed system according to the concepts of topology. It must possess periodic orbits with noticeable density. Following is a list of chaotic dynamics. Sensitivity to initial conditions. Sensitivity to initial condition means that each point of a typical chaotic system is closely related with other point in different future paths that are known, or trajectories. Thus, it is derived that if trajectory faces even a small change, future path is likely to be affected at a much higher level. And the amount of the modification is high too. Because of the modification of future path, future behavior will change too. As described above, sensitivity possessed by initial conditions are referred as butterfly effect. This name has a historical reason. In 1972, Edward Lorenz submitted a paper to American Association for Advancement of Science. The title of that paper was, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" In the title described, flapping wing represents the initial condition is facing a small change, that is causing multiple subsequent events that are able enough to initiate a phenomena of large scale. If the butterfly had not flapped its wings, the status of initial system might have been different. If a finite amount of information is taken about the system in the beginning of the process, then after a certain time had passed, the system will not remain as predictable as it used to be. This is a consequence of sensitivity to initial conditions. This effect can be observed in cases where prediction can be made about a week ahead. Weather can be a great example to understand this effect, since it can be predicted 1 week ahead or even more. This does not mean that it is completely impossible to predict about events that are likely to happen in far future. However, there are some heavy restrictions to do so. For instance, using weather prediction, we can determine the lowest and the highest possible temperature throughout the year, but we cannot define exactly which day is going to be the hottest or the coolest day for that very same year. Sensitivity of initial conditions can be measured according to a mathematical term named Lyapunov exponent. To do so, two starting trajectories in the phase space are assumed. These trajectories are infinitesimally close. In the equation, t represents time and alpha represents exponent of Lyapunov. Orientation of the initial separation vector determines the separation rate. This is the actual reason for which Lyapunov spectrum exists. The number of dimensions is derived from the number of Lyapunov exponents, since these both are equivalent numbers, which means both have same values or count. If number of dimensions and Lyapunov exponents are different, then large one is preferred more. For example, maximal Lyapunov exponent, which is known as MLE, helps to derive the predictability of any system. If the value of MLE is positive, the corresponding system is considered chaotic. Measure theoretical mixing and K-system properties are great examples of other properties that correspond to initial condition sensitivity. Topological mixing. Concept of topological mixing is also known as topological transitivity. Topological mixing means that with the flow of the time, the system will evolve with it. It indirectly means that existing open set or regions will be overwritten with any other new region. These regions, or open sets, corresponds to phase shape of the very same system. Mixing is a mathematical concept. According to the concept of mixing, standard intuition and colored eyes or fluid mixing are examples of a chaotic system. In chaos theory, topological mixing is referred multiple times. It describes that chaos corresponds only with sensitivity found in initial conditions. However, it is impossible to define chaos by only using sensitive dependence of initial conditions. To understand this concept, refer to this example. Consider a dynamic system is developed by doubling the initial value subsequently. In such system, any pair of points will be separated as the time passes. Thus, the system will have sensitive dependence on initial value almost everywhere in the system. However, this example is not based on topological mixing, hence has no chaos. Although the behavior in example is extremely simple because all points rather than zero will be infinite value, both positively and negatively. Density of periodic orbits. If a chaotic system has periodic orbits with noticeable density, it means that periodic orbit has covered every point in that system space with a close arbitrarily approaches. Using Swarovski's theory as a base, Lai and York managed to prove that every one-dimensional system that holds a regular periodic cycle also corresponds to the regular cycles of other length. This kind of system also corresponds to chaotic orbits. This research was done in 1975 by these two theorists. Strange attractors. One-dimensional logistic map, that is a dynamic system, defined with x to 4x, 1 minus x, are said to possess chaotic behavior everywhere. However, sometimes this kind of chaotic behavior is only found in a certain subset of phase space. The most interesting cases are those when chaotic behavior takes place upon an attractor. Consequently, orbits will lead to the very same coverage of this chaotic region by a massive group of initial conditions or circumstances. Described here are the most applied dynamics of chaos theory. Other less applied, yet important chaotic dynamics are listed below. Chaotic system at its minimum complexity. Jerk systems. Concept of spontaneous order. Spontaneous order is also referred as self-organization. In chaos theory, it is the spontaneous emergence of order. This concept finds its origins in many theories such as physics, biology, social network and economics also. In biological and physical processes, this term is often used. Spontaneous order is used to define emergence of various social orders that are derived from a combination of individuals with self-interest. Those individuals should not try to create an order intentionally. Some famous examples for systems that evolve spontaneous order are listed below. Evolution of Earth, evolution of language, evolution of crystal structure, evolution of Internet, free market economy. Organizations have made spontaneous orders to distinguish. Turning into scale-free network was the main reason for them to be distinguished, since organizations follow hierarchical networks. Moreover, organizations are most likely to be a part of spontaneous social orders. Here, it is noticeable that spontaneous orders cannot be a part of hierarchical networks like these organizations. There is one thing that separates both the concepts. Humans are responsible for creating and controlling organizations. Spontaneous orders are created and controlled by themselves. They cannot be controlled by anyone and anyhow. Following the fact, economics and social studies describe the spontaneous orders are a result of human actions. They are not resulted from human design. According to the concept of emergent behavior, spontaneous orders are considered as a kind of synonym. Self-interest spontaneous order is nothing but just an instance of this very same concept called emergent behavior. History. Murray Rothbard describes that main idea of spontaneous order was presented between 369 to 286 BC. Yes, it is that old. Zhuangzi is considered the constructor of this concept. He ignored or literally rejected to accept Confucianism's authoritarianism. He believed that there has never been such thing that tried or attempted to govern humanity. Instead, he said that there has always been a concept which lets humankind roam alone and free of restriction. He managed to describe how good order is developed automatically and spontaneously when we let the facts let alone. Later, this concept was developed further by Proudhon. In the field of market, first every serious studies of spontaneous order were done by the theorists of Scottish Enlightenment. The modern concept was described by Adam Ferguson in around 1767. He also proved, with different approach, that phenomenon of spontaneous order is the result of human actions. They cannot be developed by executing any human design. This concept was later refined by Austrian School of Economics. This school was led by Karl Menger, Ludwig von Mises and Friedrich Hayek. They managed to get this concept at center of their social and economical fields. Following are some examples of spontaneous order in various fields. Game studies. Modern game studies share a strong connection with the concept of spontaneous order. In 1940s, important results were disclosed by Johann Huizinga. He wrote that forces of civilized life share their origins in both myth and rituals. He termed civilized life as massive instinctive. He also wrote that law, order, commerce, profit, craft, art, poetry, wisdom, science, etc. all are the roots of soil of play. Following the results of book named The Fatal Conceit, Hayek also presented his thoughts about this concept. He termed games as instance, in fact, clear instance of a progress. He said that in such progress common rules are followed by all participating elements, their conflicting different purpose to result as overall order. Markets. Hayek is one of those many liberals who argue that market economics indeed is spontaneous order. He also claimed that economics are superior order than any other order and humans cannot design great model than this due to lack of specifics and information. This information or specifications cannot be derived from statistical data because statistical data is gathered by abstracting the particulars away from the proper situation. According to the concept of market economy, price can be aggregated from required information. There is only one condition, that people must be set free to use their individual knowledge rather than derived theory. Everyone is then allowed to deal with commodity or substitute in order to make decision. This decision will be based on more information than an individual person can personally gather. It means that information cannot be conveyed using a statistical centralized authority. Any interference made by central authority will affect the price, since no one will have information about all the particulars involved. Anarchism. Many anarchists argue that state is artificially formed by ruling elite. They also think that if eliminate these ruling elite, true spontaneous order would arise as consequences. According to anarchist perspective, voluntary cooperations of individual particulars would be also involved in such constructed order. Oxford Dictionary of Sociology describes that according to anarchist vision, it is compatible if multiple symbolic interactions combine their work. It also refers spontaneous order to be a particular view of society. Sobornost. Russian Slavophilia movements and Fyodor Dostoevsky's work describes the concept of spontaneous order briefly. The main concept of organic social manifestation is described under the concept of sobornost as a concept in Russia. Leo Tolstoy used sobornost as a base in Christian anarchism ideology. Uniting force behind the peasant, Serfovshchina in pre-Soviet Russia is described using the concept of sobornost. Recent developments. Friedrich Hayek is said to be the most famous researcher and theorist in the field of social spontaneous orders. He made an argument in which he said that common law and brain are two separate types of spontaneous orders. He termed this argument as catalexy. In the Republic of Science, science was described as a spontaneous order. Michael Polanyi was the one who made such argument. This concept was further pursued and developed by Bill Butos in multiple papers. Thomas McQuaid also contributed a lot with his work on these researches. History of chaos theory. Henry Poincare is said to be the earliest proponent in the field of chaos theory. Henry Poincare was pursuing studies in three-body problems in early 1880s. During that time span, he discovered that some orbits could be non-periodic. He also found that such orbits do not increase infinitely or they approach a fixed point. In 1898, an influential study of chaotic motion was published by Jacques Hadamard. The motion he studies was of a free particle that is frictionless gliding on a surface. This surface tends to have negative curvature. Such a surface is known as Hadamard's billiards. He managed to prove that all trajectories are unstable. Ergodic theory was the first field to provide a start to the concept of chaos theory. Subsequently, George Birkhoff pursued studies of chaos theory in the field of nonlinear differential equations. Following is the list of every researcher included in that research. George David Birkhoff, Andrei Nikolaevich Kolmogorov, Mary Lucy Cartwright, John Edensaw Littlewood, Stephen Smale. However, they could not successfully observe chaotic planetary motion. Non-periodic oscillation in radio circuits and turbulence in fluid motion were encountered by many of these researchers. However, they could not describe it properly since they had no proper theory to tell them what they were actually looking at. Chaos theory failed to be formalized in the early 20th century, despite of multiple initial insights. The complete formalization of chaos theory was done in pre-20th century. It became possible when some scientists observed that linear theory failed to describe obtained behavior of certain experiments, such as logistic map. Linear theory was considered a prevailing system theory of that time. Noise was attributed as measure imprecision and considered as a complete component of corresponding system according to theorists studying in chaos fields. Simply refer to them as chaos theorists. At that time, they were not known as chaos theorists since there was no fully developed chaos theory. Electronic computer acted as main catalyst in order to develop chaos theory. Repeated iteration of simple mathematical formulas is included in mathematical concepts of chaos theory. Such iteration is impractical or even impossible to do by hand. With the help of electrical computers, the task of iteration was made practical and easy. Figures and images helped to visualize the sunning system. Random transitional phenomena were discovered in 1961. However, they were published in 1970. This phenomenon was discovered in Chihiro Hayashi laboratory that operates in Kyoto University. These phenomena were noticed by Yoshisuke Ueda, a graduate student on 27th November in the year of 1961. However, his advisor did not agree to disclose the researches without solid explanation and proofs. The concept was finally disclosed in 1970, with proper description to explain the very same concept. Yes, it took almost 9 years to find explanation for a fact that was already discovered 9 years ago. In 1979, Pierre Hohenberg organized a symposium. During the very same symposium, Albert J. Liebschaber disclosed his experimental observations. In his researches, he observed bifurcation cascade. It was proven the very same concepts that led to successful implementation of chaos in Rayleigh-Bernard convection systems. For this useful research in the field of chaos theory, following researchers were awarded Wolf Prize in Physics in the year of 1986. Albert J. Liebhaber, Mitchell J. Feigenbaum. New York Academy of Science joined its operation with National Institute of Mental Health and the Office of Naval Research. It was the first ever conference based on chaos in the joint field of biology and medicine. It was formed in 1986, in which eye tracking model was presented by Bernardo Huberman among schizophrenics. As consequence, physiologies were updated or say renewed in 1980s with implemented applications of chaos theory. For instance, studies of pathological cardiac cycles were included in the field of physiology. Distinguishing random from chaotic data. In practical implementation or research, no time series is contained with pure signal, which makes it difficult to tell whether physical or other kind of process is random or chaotic by only using data. It is hard to get pure signal to do so. Despite the sound is preset as truncation error, some form of corrupting noise is most likely to be encountered. Thus, it can be said that any kind of real-time series contains some randomness, even if it is deterministic. Almost every method used to distinguish deterministic and stochastic processes are based on a simple fact, that any deterministic system makes progress in the same way it did at given starting point. Further, one can follow given process if a time series is provided for test. First, consider a state for testing purpose. Second, compare and find a time series with the nearest possible state. Third, compare time evolutions of both states. The difference found between time evolution of determined state and nearest possible state is defined as error. Error found in any deterministic system tends to remain small or keeps incrementing as the time passes. The increasing error level is said to have chaos behavior. Generally, almost every measure taken to determine time series is dependent on the difference between closest state and given test state. Correlation dimension and Lyapunov exponents are great examples for this fact. One have to depend on phase space and methods such as Poincare plots to derive and understand state of a system. To do so, one needs to consider an embedding dimension. Using the dimension as a base, propagation between two nearby states is investigated and explained. If the error tends to be random, the dimension level is increased. At such point, if dimension can be increased, the analysis is done because one can easily determine error by increasing it. It may sound very simple, but it is not. Because as the dimension is increased, the data and calculations required are increased constantly in order to derive a suitable and close candidate as well. If the dimension level is kept low, deterministic data will tend to be random. However, in chaos theory, there is no restriction to keep the dimension at a higher level. The method will work the same with any level of dimension. If an external fluctuation attend a non-linear deterministic system, serious and permanent distortions are much likely to encounter by its trajectories. Moreover, the inherent non-linearity causes noise to be amplified. It turns out to reveal very new dynamic properties. There is a huge risk of failure included in attempt and experiments to separate noise from the deterministic skeleton or to isolate the deterministic part. The situation becomes harder if the deterministic component turns out to possess a non-linear feedback system. When interaction between non-linear deterministic component and noise takes place, it results as displaying non-linear series. This non-linear series is able enough to derive dynamics that are used to test non-linearity. Such results are sometimes not achieved or derived. Philosophy also describes how deterministic chaotic system can be distinguished from stochastic system. It has managed to prove that these two aspects are most likely to be equivalent in observational perspective. Applications of chaos theory. In the beginning era of chaos theory, it was mainly used in order to observe weather patterns. Nowadays, it is also applicable to other various situations too. Following is a list of fields in which chaos theory is proven applicable in a proper manner. Geology, mathematics, microbiology, biology, computer science, economics, engineering, finance, algorithmic trading, meteorology, philosophy, physics, politics, population dynamics, psychology, robotics. Despite of containing a noticeable number of fields, this list cannot be said a complete or comprehensive list since research is still going on and many new fields are proven eligible to apply chaos theory. Some of the important fields from list above are covered below. Computer science. Use of chaos theory in computer science is not a new concept, since it has been practically used since years now. It is also described in cryptography. Chaos theory models an encryption, secret or symmetric key that operates based on diffusion and confusion. Information in image or any other form can be encrypted more efficiently by implementing chaos theory in DNA computing. Chaos theory also provided benefits to the fields of robotics. In traditional robotics, robots interact with their surrounding in a trial and error type model. Such model had its own limitations. Chaos theory was used to build a predictive model which is considered as an important revolution in the field of robotics. Biped robotics also managed to take advantage of chaos theory. Chaotic dynamics were used in order to develop passive walking biped robots. Whole concept of passive walking was based on this particular theory in the field of robotics and especially biped robots. Biology. Since hundreds of years, population model is being used by many biologists. The purpose of population model is to keeping track of population of various species. Almost every population model was considered continuous until scientists managed to implement population models with chaotic behavior for various species. Population model of Canadian lynx is a great example for such behavior, since it was observed that the population of this particular species possessed chaotic behavior. Chaotic behavior was also observed in various systems of ecology. Hydrology is a great example of ecological chaotic behavior. Many scientists argue that there is much left to learn about hydrological behavior from perspective of chaos theory. Cardiotocography is another example for application of chaos concepts in ecology. To obtain accurate information, fetal surveillance is used as ideal balance. The process is enforced to be non-invasive as far as possible. Chaotic modeling allows getting better models of warning signs that are a part of fatal hypoxia. Application in other fields. In the process of manufacturing polymers, it is essential to predict solubility of gas. In such process, wrong points are much likely to be covered if particle swarm optimization (PSO) is used. Implementation of chaos allowed developing improved version of PSO. This update version allows the simulation to keep flowing without being stuck at any point. In celestial mechanics, asteroids are observed in order to predict their behavior, such like when they reach Earth or other location, etc. Applying chaos theory in such observation allows getting better predictions about behavior of such asteroids. As known, Pluto has 5 moons in total. 4 of these 5 moons are observed rotating chaotically. Chaos theory is also used in quantum physics and electronic engineering. It is used greatly in studies of large arrays present in Josephson junctions. Coal mines are always dangerous since natural gas leaks often cause many deaths. It was tough to predict that exactly when they occur. Recently it had been proven that these gas leaks tend to possess chaotic tendencies. If scientists manage to model these tendencies properly, gas leaks are much likely to be predicted with noticeable accuracy. This theory is applicable even outside the concepts of natural science. A model for career counseling can be determined by including a chaotic interpretation of the relationship exists between job market and its employees. This model will help a lot to provide better suggestions to those people who are struggling to make appropriate career decisions. According to theory of chaos, organizations are complex adaptive systems. These systems are said to contain natural fundamental structures that are non-linear. These structures correspond to various forces. These internal and external forces are said to be the source of chaos. In the field of verbal theories, the chaos metaphor is used. To describe small work group complexity, mathematical and psychological aspects are proved related to human behavior. These aspects are used to derive useful insights to study complexity of small work groups. This kind of research takes the concept beyond the concept of metaphor itself. Traffic forecasting also receives great help from applications of chaos theory. It allows to predict various kinds of behavior of traffic, like when traffic will start and what level it will possess, how thick it will be, can be predicted before its occurrence by applying chaos theory. A basic overview of broad chaos theory was provided. You should have already got an idea that chaos theory was all about predictions and its accuracy. The applications of chaos theory are not limited as showed in the final chapter, since many researches are going on in order to make it possible to apply chaos theory in more and more fields. Until the date, most of the scientific fields are proven applicable of chaos theory. Many are still to be proven. However, chaotic behavior is very common to find in any field of studies and researches. All theorists need to do that to find practical proofs in order to prove the observation legit. Late 20th century was proven a huge bang for theory of chaos. As it can be seen in the chapter about theory, many major researches are done in the time span of late 20th century. Most of the modern researches are following the researches done in previous century. Thus, it can be said that base of the chaos theory was constructed in that span of time. Researchers are still trying and putting their efforts to take this theory at a next level with more accurate and legit results.